I'm Steven, that's Justin. Nick and Ricky are both online. They're both virtual. We made a programmable delivery bot. Our team is a lawnmowers, and clearly that is not a lawnmower, so different basis now. So I'll let Ricky discuss sort of the purpose, and then Nick, it will go into the overview and materials.
Sure. So the purpose is that the recent pandemic has now made life easier for those who care about transmission of disease, especially resulting from delivery services. Our project intends to serve the purpose of offering hospitals, senior homes, and other co-living spaces the provision of robust, contactless, and autonomous delivery. The recent global pandemic has only reinforced the necessity of minimizing contact touchpoints during deliveries as soon as possible. And now to discuss our project overview and materials, Nick's going to take over.
All right, so our delivery robot basically offers a template for future robots that would be able to perform contactless delivery services, whether it's like food delivery, medication delivery, and so on. And it comes equipped with real-time path correction and alignment, a sensor array for object detection, collision prevention using snap action levers, and the capability to load pre-existing route files that are saved onto the robot and create new and additional routes. And so we have a list of materials which includes both software and hardware components. For our software, we use the Genie and Arduino IDEs as our code editors. We used PuTTY as our SSH client so that the Raspberry Pi terminal can be accessed from another computer on the same network. And VNC Viewer as a remote access application so that our remote team members can access the Raspberry Pi from their own computers. And as for the hardware, we had a Raspberry Pi 3B, a Teensy 4.0, and we had our infrared distance sensors and Pololu snap action levers, which work together as our collision prevention, an IVT2 DC motor controller, and 99-to-1 metal gear motors. And only one of these gear motors had a rotary encoder, since it didn't really make sense for both of them to be sending distance data to the Raspberry Pi. And then we had 6 rechargeable 3.7 volt lithium ion batteries and a Raspberry Pi battery pack. And all of these were mounted onto our chassis, which came equipped with treads. And so we decided to have treads so that the robot could better handle bumps in the terrain or any unevenness in the floors. And now I'm going to be handing it off to Stephen.
Well, actually, we'll go to Justin and talk about the block diagram first. So.
Okay. I'm not sure how well the block diagram is visible, but basically what we have here in the system is it's run by a Raspberry Pi 3B. So the Raspberry Pi kind of controls the GPIO functions that control PWMs to the motor control drivers for both of the motors. Since the motors required higher current, we had to update them to different motor drivers, and we needed a total of 4 PWMs to control each. They were a little bit undesirable, but it's what we got at the time to make it functional. So they work in tandem where each motor for a reverse and forward function takes 2 separate PWMs. You just can't have both sending at the same time. So you turn one on and one off in order to drive the motor in the forward or reverse directions, which are sending through somewhere around 1.5 to 2 amps worth of current, which is one of the reasons we had to go to a much higher voltage motor control driver. So the GPIOs are controlled on the Raspberry Pi, and we're running that through a C program or a C++ program that was written to maintain and control GPIO functionality. In order to drive the vehicle forward, we also capture rotary encoders on one of the motors, which gives us counts and distances to a pretty relatively accurate threshold. We found that it could get accurate distances up to about plus or minus 0.0, 0.1 inches. So over longer distances, that would end up being a little bit of an issue, but for testing purposes, it wasn't. The main functionality of it, though, is our controls sensor for the forward driving function. The forward driving function utilizes a BNO, which is connected to a Teensy 4.0. So the BNO is going to capture real-time yaw angle data on the x-axis. And when the program itself is turned on, it's going to capture an initial reference point for a north heading, and it'll create cardinal directions for east, west, and south that will retain throughout the function of the program. So as the program rotates, like the vehicle were to rotate in a position, it would have new set points for its new headings. So as the vehicle would drive forward, it would utilize the control settings. We implemented a PID controller to keep it to the set point angle, and it works relatively well. A lot of the issues and constraints are with it's not working and functioning as quickly as we want, has to do with the motors and the chassis and the tightness of the tracks itself. Also connected to the TNC 4.0, we have a sensor array, which includes 2 push-button sensors for interrupts to detect objects that are physical and are easily missed by the infrared sensor, and the infrared sensor itself, which can detect objects up to about 2 feet in distance, which will suspend the program if objects are detected and wait for the object to be removed in order to continue running itself. And the main issue we had with the analog, the sensor itself, the infrared sensor, was analog, and the Raspberry Pi doesn't contain onboard analog to digital converters, so we opted to run a separate microcontroller just for sensor input and use digital interrupts on the Raspberry Pi to control the interrupts that would happen if objects were detected. And
So I'll discuss some of the engineering challenges that we kind of faced during this project. So one is back at the beginning of the semester when we first started this device, we didn't really figure that, like, you know, with any given floor, these devices, like the slightest little like jolt or like ridge, it's gonna throw the whole device off, and then you go 10 feet, you're gonna be off 3 feet to the left because of one little small like interference you had. So the main thing we implemented on this was the control system, as Justin talked about. This helps it stay nice and aligned, so you know you can bump it off its axis, but it's still gonna find that center point and keep going forward. Another thing was accurate distance measurements. So we spent a lot of time looking at the rotary encoder and, you know, how many counts translated to how many feet it would go forward. So if I remember properly, it's around 2,050 was the amount of counts that that device is going to take to, you know, go 1 foot with the rotary encoder data. Another thing is, as far as the motor specs, there's a lot that goes into picking those motors, because before we had this device, we didn't know how tension that those tracks were going to be. So we just bought 6-volt motors, and that did not suffice at all. Couldn't even move it. So we had a few problems there. We had to buy higher voltage motors in order to power that device. We also needed a user-friendly menu, because all of us in this room could probably navigate a program pretty well, but this device is going to be typically used just about anywhere. So you're not going to have someone in a senior home knowing how to operate software very well. So Justin implemented a very user-friendly menu. It's going to make it really easy for anybody to sort of pick up the device, create a route, load an old one, exit. It's going to be pretty flawless in terms of anybody picking up the menu. Another thing we had was a sensor thresholding. So we weren't quite sure how far we wanted it to, you know, stop, or like how close someone wanted to be. Then there's also the thought where if you have this device going and someone steps in front of it, the sensor might stop it, but if the sensor just stops and then when you lift your foot back up, it keeps going, it's likely just going to catch up to you if you're someone who's walking very slow or someone with like a cane or something. So we need to make sure we had that sort of like interrupt where it waited a second and came back and then continued the device on its path. So, and then one other thing is we had to sort of deal with this chassis, which has been, for lack of better words, utter sort of disaster, I guess, because we're not mechanicals. So there's a lot of stuff that goes into these sort of like design aspects that we weren't really aware of before we picked it up. Granted that this device still works to its full functionality, but there's a lot of things that we needed to consider mechanically that we didn't really perceive in the beginning. We thought we kind of just, you know, make a device and get going, but that's not really how that goes about it. So there's a lot of stuff that had to go into that chassis to really make it fully functional. And then the last thing, we had to develop software for creating routes and also loading routes. So if we'll show later on in the demo, like how it exactly, you know, creates a new route, and then when it's reading from that route, what data is it processing, and, you know, how is the file written when you actually make a new route or you load one. So I guess we can get into sort of demoing this device. If you want to pull it up on your computer, Justin.
So essentially, I've logged onto the Raspberry Pi over SSH, and we just run a simple demo program. So initially when it starts up, here you can see that it's using the B&O and it grabs the north heading for the angle on the axis, and then it creates cardinal directions of reference points. Because when it's going to rotate, it's not going to use any kind of control systems to get an accurate rotation. Rotations end up with like a plus or minus like 2 to 3 degree error. So the idea is that when it starts driving forward again, it has a set point already and it'll just correct itself as it drives forward. So we'll jump right into the the main menu in here, and we'll jump into the...
Yeah. So let me just get this. So originally what our plan was is we were going to demo in that room. So we had all these routes programmed, but seeing as you can't fit 30 people into that small room, it's a little bit different now. But when we open our menu, you'll see that there's like 4 rooms per se. But for this case, we're just going to show off it going from room 1 to room 2 and then back to home. Originally, it had 4 different routes, 4 different rooms. You could go to any different room from any set point. So if you're at room 2, you can go home. You can go to room 3. You can go to room 4. You can go to room 1. Doesn't really matter. One good detail with this too that we implemented was with this whole demo, you can't kill this program until you're home. Because you don't want this device getting up to like, some door and then just, someone quitting the whole program and then having this device just sitting at the front door. So you can only quit this whole demo once it actually gets back home. So that's another good thing. So here, just,
Yep.
here,
And we opted out of the using the longer length rooms because it's really slow. And if we had it driving to one of the further away rooms, it could take almost like 2, 3, 4 minutes just to get there. So for the demo's sake, we'll start the PDV demo, and it has a selection here. It says that we're currently in the home location, and we can move to any of one of the 4 rooms, and we'll move directly to room 1. And the vehicle, we designated the tape strip here to be room 1, and that strip there should be room 2.
and just to exhibit the sensors work, if you stand in front of it, stops, wait a second, it'll go again. You hit this bumper, it'll stop, it'll go again. And if you can, I don't know if you guys can see it, but it was slightly off when it turned, and then it recorrected itself
Yep.
to go back to this room, because it just takes those cardinal angles that Justin talked about.
Oh, it's detecting.
It might detect your, the infrared might
It
detect
does.
your camera.
Okay.
So, but one thing you can see here is that Justin implemented a part of the program where when an object's detected, this is going to tell you. So, like,
Yeah.
if someone's in like a room and they just sent the device out and if they have this whole module open, they're going to see that if it's like an object's detected and it hasn't said object removed, like they can go out and be like, oh, so this device is still standing still for like the past few minutes. Let me go check to make sure that there's nothing in the way of it, and let me go move something if there's a box or something. So that's just another good touch.
Okay, and then now the menu itself updates, and we're now at room location 1. And we have the options to return back home or go to room 2, 3, and 4. In this case, we're going to room 2. So the vehicle's going to run pre-programmed routes that we have, and we design for it to travel from room 2 to 1. So you can see how slow it is. We wouldn't want it driving
40
across
feet.
the room. We'd be here forever. That is about as fast as it can go due to the necessary torque needed to turn the tracks. There's so much tension on there that that's about as good as the motors can get. Okay.
So now we'll just send it home.
Yep, we'll send it back
as you
home.
can see in this menu, there's no like quit button here. You have to send this thing home, or else you're just gonna sit there all day.
So every route that it's actually performing is a loaded text file. We've encoded all the data very simply onto text files. Text files are loaded, they're parsed for data, and then functions and commands are created from that are parsed back.
Yeah, that's what I was
Flavoring
thinking.
And it'll spin around.
And so as you can see, obviously it's not exactly in that box,
Yep.
but that box is more of just a reference point for when you restart the device back up, so it can like it makes sure it goes to like a pretty precise spot in the room.
It's not perfectly oriented after turning around because there's errors in all the rotations, but they'll be corrected as the vehicle drives forward again. Now that we're at the home location, we can quit the demo menu and return back to the main menu here. And we will demonstrate creating creating routes, we created a simple function where you can create routes forward, left, and right with distances. And then upon completion of a route that you design, there's an option to create a reverse route. So whatever route you make to a location, a reverse route will be made to send it right back to the location that it originally. We'll demonstrate that.
One more thing too. So if you see on our menu, you also have this reset vehicle function. So one thing, if you move this device around a lot, sometimes it's going to have its angles be off. So, and when you do that, you're going to get a bunch of error mismatches, and it's not going to know exactly where to go. So a good way to do that is when it gets back to home, you have this reset vehicle, you put it in its spot, you reset it, it's going to give you the angle measurements again, and then that way you know if you try to rerun it, it's not going to have these error mismatches or anything that sort of just throws it off or has it turn right for no reason at all.
If you can.
So we also figured that it'd kind of be useless if me and Justin showed you how to create the menu, because the whole part of this is that Justin's menu is pretty easy to use. So if someone wants to come up and try to create menu themselves, feel free. Does anyone want to volunteer?
Yeah. I don't really think anything can go wrong, but you never know.
Over there.
Hey, so you just do create route. Here, you just hit enter. Everything functions off of arrow keys and enter unless it specifies. In this case, they'll have you enter a file name for a text file. You can name it whatever you'd like.
Oh,
Most
okay.
likely it's not. Our save file folder should be empty at the moment.
Route 1. Enter.
And then it will give you a selection of commands. So you can go forward, you can enter distance in feet,
Okay.
and it'll ask you if you want to enter more actions in.
Do you want me to do more than one?
Yeah,
Okay.
just, I guess do like a right and then
Go right.
and then select another one, and then maybe forward 5 feet.
Yeah, that's
So it's not too far, we're not waiting too long for it to drive around. And now if you hit no for another selection, it's gonna ask you if you wanna create a reverse route. If you hit yes, it will create 2 text files, one for the original route, and one to send it back home from wherever it is.
Enter.
Yep, enter and continue. So now,
Wow, that was very easy. Very user
Thanks, Nick.
so if we go to the load route function now, the only thing present in there are the text files that are considered routes. So it's dynamic. As he adds more routes, it'll expand and you'll see more files. It's just reading like a simple directory. As you can see, he has the route 1 text that he created there. So if we run that, the vehicle will do exactly as he specified. It should go 10 feet, turn right, and 5 feet, stop. And if I run the reverse text file that was created for it, it should send it right back to where it was. Provided the pins don't pop.
I just want to just check them.
Okay. And sometimes there's, the infrared can pick up some phantom.
It might pick up stuff from the cameras now I think of it too.
Yeah, and sometimes the lighting too. It has known to pick up some of that. Okay. And now that that's done, if we run the reverse route, it should turn around and return right back to where it started.
Yeah.
Yeah, it's slow. So it's pretty accurate, not 100% there.
So I guess just to wrap it up, as far as this being the full-blown like device that's ready to ship, that's not the case.
No.
This is if you want to use a medical delivery device. We know that obviously medicine can be people can abuse medicine, people can lose medicine, all this sort of things you don't want to happen. A future implementation would be some sort of like a locking device where it only unlocks once it gets to the room. That way, if someone's just walking along, sees medicine sitting on it, they can't just take it off the thing. Obviously, better motors would be a good idea in the future so this thing moves faster. Maybe some sort of sort of system that tells you when you get to the room to make sure you're there. Maybe just so it doesn't get stuck or something like that. But yeah, those are just some future improvements. Anyone have any questions? All right, thank you.